So I'm going to talk about the tides. The topic title is the tides, the familiar unknown, because tides have been observed by people for centuries and millennia, but still there are not many things that we understand about tides completely. So that's the reason why this particular uh, talk has been given this title, The Familiar Unknown. So what you're seeing on the screen now is the planetarium, Jawaharlal Nehru Planetarium in Bangalore. This is the place where I work, and it is dedicated to the cause of science education in general and astronomy in particular. And on the top right of the screen, you see my email ID. So if you wish to correspond with me either about this talk or about science education in general, you can please feel free to email me on this account. Now, there is a very strong connection between the moon and man. Of course, man to represent the entire humanity, so there is no gender bias as such. But the moon-man connection dates back to as old as humans have been able to look up into the sky and marvel at the moon. Now, this particular quotation, which I like a lot, is very relevant to the talk that I'm doing today. This is a wonderful quotation by Mark Twain, who said, "Everyone is a moon and has a dark side which he never shows." So here, Mark Twain is actually drawing a parallel between the moon and the human behavior. And I must say that even though there is a metaphoric reference to man and the moon, and the dark side especially, in a literal sense, moon has a dark side which it never shows to us. Unless you are willing to leave the planet Earth and go around the moon, you will never be able to see the dark side. It's only called a dark side only because that side of the moon is not visible to us. But otherwise, sunlight does fall on that part of the moon also, and that also shines as bright as the side that faces us. So Mark Twain was born in 1835, November 30, and he passed away in 1910, April 21. But the reason why I'm mentioning about his date of year of birth and death is that these 2 years actually mark the apparitions of comet Halley. In fact, he was born on November 30th, as you see on the slide, and it was just 2 weeks after Halley's comet had come closest to the sun. And then he passed away in 1910, just 2 days after comet Halley had again visited 75 years later and come closest to the sun. So there is some kind of a connection between Mark Twain's lifetime, his birth, death, and Halley's comet. And as we shall see, Halley's reference in this context is not just a poetic reference. Halley figures in our discussion about tides and about whom we will be coming across a bit later in some detail. So the dark side of the moon, Halley, and the tides, there's a strong connection, and this talk is all about how this connection comes about. So here you are seeing a picture of the moon. It's a composite picture taken of moon throughout the month, and you'll find that the front surface of the moon, the face that which is towards the Earth, is always the same, no matter what phase of the moon that you are looking at, whether it is a crescent phase or whether it is a full phase or it is the gibbous phase. It's always the same side of the moon that is always turned towards the Earth. Now we are able to find out that it's the same side of the moon that is facing the Earth only because moon has certain surface features which act like markers. Whereas if you look at the changing face of planet Venus, which has no such markings on it, at least when it is taken through photographed with a low resolution camera, you cannot make out whether Venus is rotating or not at all. Because in every phase, face of Venus, which is towards us, appears the same. So, whatever markings that are there on the surface of the moon is a very good marker for us to infer whether the moon is rotating or not. So people who observed moon from the earth for centuries were always puzzled as to why we see the same features on all days of the month and month after month. And it took some time to realize that it is as though the moon is not rotating at all, because a rotating moon would have shown slightly different markings on it during the course of a month. If you could actually leave the Earth and go to the moon in a spacecraft, and if you went around, you can actually see the dark side of the moon, which is marked on the right-hand side of the bottom picture. So there are craters, just like you see craters on the side facing us, but in the overall details, the other side of the moon, which we call the dark side, is slightly different from the side that is facing us. But that is not the point of concern to us in this particular presentation on tides. Edmund Halley, he studied ancient eclipse records. So he was trying to calculate. From the present data as to when certain total solar eclipses happened in a particular place in the past. What he found, his surprise, was that there was a systematic shift in the longitude where the total solar eclipse had taken place. Now, longitude, this is related to time. So Halley thought either there must be some variation with respect to the time measurement as done in his time and time measurement as it was done in the past, or there must have been a systematic shift in the longitude of the place. Now, the second factor can be ruled out. There is no reason to believe that there is a systematic change in the longitude of a place that comes on the globe. So, he was worrying about why there was a difference between the time that he calculated for total solar eclipse in a particular place in the past with what had been documented in the record. Then I come to another one, which is completely unrelated to eclipses. What you are seeing on the bottom of the screen are 21 or so pieces of comet Shoemaker-Levy, which were torn apart by planet Jupiter as the comet went very close to Jupiter. Now, what has this in common? The comet breaking up into pieces, Halley observing anomaly between the calculated time of eclipses in his time and in the past, and we looking at the same side of the moon all the time. Now, the point that connects all these three seemingly unrelated phenomena is the tides or the tidal force. So, rest of my talk will be trying to link how these three seemingly unrelated phenomena are actually brought about by tides that happen on the Earth. And to keep matters very simple, I'll be discussing mostly about the ocean tide, which is the most visible part of the tidal effect, and see how, in principle, understanding these ocean tides will help us to understand the anomaly that Edmund Halley observed, and why we see the same face of the moon all the time. And the third effect, that is a breaking up of comet Shoemaker-Levy by planet Jupiter as it went close to the planet. Very often, people mistake the rising water waves near the seashore for tides. So you see in this picture a wave which is raised up and then moving towards the seashore. Very often, people mistake these to be the tides, but actually they are not the tides. These are water waves that rise and fall within a few seconds. So the height of the wave is retained for not more than a few seconds before it falls back onto the ocean. But when we talk about tides, we are still talking about rising and falling of the water level in oceans, in seas, and in large rivers. But this variation in the water level takes place over a period of several hours. So in this picture that you see, on the left-hand side of the picture here, you find a lot of water. On the right-hand side, it looks almost barren without any water. This is a picture of the same place is taken 6 hours apart. So again, 6 hours later, again you will find a lot of water here. So this water level increasing and diminishing in a particular place happens over a period of a little more than 6 hours, and this is what we refer to as ocean tides. So tides or tides broadly refer to some phenomenon. It is also an effect, and it is also a differential force. So there are these three aspects of tide, and during the course of this talk, I shall be discussing all these three aspects of the tide, especially with consequences in astronomy and surprisingly consequences in biology. I'll try to play this video. I shall try to play this video. Hopefully, it will have enough bandwidth to play in real time. This is a place called Bay of Fundy in Canada, and you find that water level is gradually going down. By the way, this is a time-lapse video, meaning what you see here in a few seconds did not happen in those few seconds in real time. It actually took several hours. So the photographer or the videographer has taken snapshots every few minutes and put them together to make this video. So you find that all the water has gone down, and now again the water level rises up. So this is the kind of change in water level that we refer to when we talk about tides. Now, while tides are visibly very striking phenomena, people can observe, especially people in seashore, fishermen, or people in the past who had inhabitation very close to the seashore, would have definitely observed the rise and fall of ocean levels periodically. So observation is not at all a difficult point when it comes to tides, but understanding the cause of tides is not at all an easy one, and it has tested the most intelligent brains over the last several centuries. Now, what are the reasons for people having difficulty in understanding the tides? This is what we will see in the next few slides. Now, any theory that you come up with to explain tides must address these three questions. Number one, what is the force which is responsible for increasing and decreasing the level of water? After all, when in a particular place the ocean level goes up, it is as if the entire water mass has been lifted up by some kind of a force. And without that force, water cannot do work against the gravity which is acting all the time and pushing it closer to the center of the earth. Therefore, we must identify an agency of force responsible for the tide. Then the second point is the theory should account for the time varying magnitude of the force. Now, if the force that is responsible for lifting this water up and then putting the water level down, it is not a one-time affair. So there is a periodicity in the rise and fall of water level, which means there must be correspondingly a force which is also periodically increasing and decreasing both in magnitude as well as direction. So theory to explain tide must also take this into account. And third part, I say lastly, but that is not the last one exactly. But the third very important one is that a systematic shift in the time of a high tide or a low tide from one day to the next should also be addressed by the theory. Now, people who are very close to the seashore would know this. I have this data about Malpe. Malpe is very, very close to Udupi. Poornaprajna College Udupi, which is hosting this particular program webinar, is very close to Malpe, about 65 kilometers from that place. I would like you to pay attention to this timings of low tides and high tides. By low tide, we mean the lowest level of water from the mean level. By high tide, we mean the highest highest level that the water achieves from the mean level. So you'll find that today is what? 18th Thursday. Just about an hour back, there was a high tide in Malpe of a height of about 1.32 meters, as you can see from the table. Now, having achieved the high tide, now the level of water is diminishing and it will reach a low at about 4:20 p.m. today. So there's a time gap of about 6 hours. And from low tide, again to reach high tide, which is at 9:03 p.m. today, tonight, it's again another close to 6 hours. Right? Now, if you look at the same low tide and high tide timings on the next day, that is tomorrow, Friday, you will find that low tides don't occur at the same time as it occurred today, and high tides don't occur at the same time as it occurred today. So there is a shift in the timings of low tide and high tide. So any theory that explains tides must also be able to explain why there is a variation in time from low tide to high tide of the order of 6 hours. And secondly, from one low tide to next low tide, the next day's low tide, why there is a shift in the timings. These are very important and crucial points to be addressed by any theory. But remember, it's very easy to talk about the rise and fall of water being brought about by some kind of a force. But the notion of the force itself came in a scientific way, in a measurable way, in a quantifiable way, only by Newton's time in the 17th century. So what did people think about the tides before Newton's time? Now, very often in science, it happens that you build a theory today, but in order to build a theory, you need a huge amount of data, huge amount of observation, and all these observations and data will have certain kinds of a pattern, and you try to now bring about a theory, either verbally or through mathematical formulation, which will be able to explain all the patterns that we have observed over a period of time. The Newton's law of gravitation, for example, would not have been possible without the data about the motion of the moon. So, another example is Kepler's laws of planetary motion. Johannes Kepler's group, Tycho Brahe, spent 20 long years just making observations of positions of all the planets and stars that you could see in the sky every single night. Now, putting together all the data that Tycho Brahe had gathered, Kepler was able to show that planets move in elliptical orbits. There is a relation between the distance of a planet from the sun and the time it takes to go around the sun once, the period of revolution, and so on. So without this observational data, Kepler's laws would not be possible. Therefore, even though theories take some time to be formulated, the theory will be actually preceded by a long time over which observations would be made and recorded. The tide is also one such example. So early navigators had observed the rise and fall of water levels in the ocean, and they also somehow related the rise and fall of ocean to the presence of moon in the sky. So the association of tide with moon is very, very old. So people had a hunch that when moon was up in the sky, uh, when it was passing the meridian point, there was a high tide in that place. Okay, so as far as observations are concerned, huge amount of observations had been done before Newton's time. I'll quickly go over 2 or 3 observations which are very important as far as formulating the theory of tides is concerned. Number one, Eratosthenes, who is very well known for estimating the size of the Earth more than 2000 years back, he pointed out that high tides occurred with a certain periodicity of half a day. So there will be 2 high tides in a day, that's what he meant. And he also showed that when the moon was either at meridian point or at anti-meridian point directions, these high tides occurred in a particular place. Another noted geographer and historian, he also observed wonderful pattern in the occurrence of tide. You remember the tide table of Malpe that I showed you a couple of slides earlier? He had actually made this kind of a tide table on every single day for a large number of years. And it is because of that kind of data that anybody who comes up with some theory to explain tides, we immediately go back to the observed data. So big data analysis is not something which is new, it is pretty old. Then there is this person, Pliny the Elder. He made an extremely important observation that a high tide occurs a little after the moon has crossed the meridian. But this is a very, very subtle point. There's not too much of a time gap between moon coming to the meridian and high tide happening in a particular place. The time difference is pretty small, but Pliny was able to observe even this. A good theory on tides must also take this into account. So the biggest challenge was to explain how a high tide can occur when the moon is below your feet, but the water is being pulled up. So this was the most difficult point to explain in theories of tides. And in the initial days, sun did not figure in the explanation at all, because sun is there all the time in the sky. But then tides happen periodically, high tide and low tide. Therefore, they had to look for something which was inconstant, and the moon actually fitted this particular candidacy very, very well, and that is how moon came to be suspected to be responsible for the formation of tides. So one of the first scientific approaches to explain tides was given by Galileo. Unfortunately, I don't have time to go into the details of his explanation, but it is enough to say that Galileo's explanation was a very, very clever one. And to cut the long story short, I can tell you that Galileo tried to explain the occurrence of high tides and low tides caused by rotation of the Earth as well as the revolution of the Earth. So he had his own scientific argument to show that rotation and revolution of Earth causes these high tides and low tides. Now, Galileo was a very clever man. He was trying to push in the Copernican system that sun is at the center and Earth goes around the sun, which was against what most people believed in those days. They felt that Earth is at the center and sun goes around the Earth. Now, Galileo, in the process of trying to explain how tides occur, he wanted to entirely tell people, look, here I have a wonderful demonstration of Earth going around the sun. Okay, but that was not to be. So Newton wrote this magnum opus, you see on the right hand side of the screen, Philosophiae Naturalis Principia Mathematica. He completed this in 1687, and but the seed work for writing this particular book happened in 1665 and 66 when there was a large bubonic plague, and because of social isolation that was required in those days, university where he was studying was closed and he was sent home, and that's the best thing to happen to science. So like in Corona times, we are now maintaining social isolation and distancing so that physical contact is minimized to reduce the spread of the coronavirus. The main motivation for Newton's work was also a similar social distancing very important work. One was to give an expression for centripetal acceleration, and again he used the data that people had gathered about the motion of the moon in order to arrive at the expression for centripetal acceleration. Like many textbooks tell you, Newton did not attack the problem of ocean tides directly. He did not apply the law of gravitation to ocean tides directly. He was actually trying to understand the orbit of the moon going around the Earth. And what he discovered was very interesting. He found that, okay, for completion, I have to explain this picture that is there on your screen. And this is the orbit on which the brown line, that's the orbit of the Earth. And the blue ellipse that you see is the plane of the orbit of the moon. The orbit of the moon is tilted with respect to the orbit of the Earth by a small amount, 5 degrees. And there are 2 points where the moon's orbit cuts the Earth's orbit. One is called AN, ascending node. Other is called the EN, or the descending node. Okay, so these are the nodes. Now, if you take this line connecting the 2 nodes, that is the intersection point of Earth's orbit and Moon's orbit, we would expect it to be a constant one. Newton showed that this nodal points actually presets, they actually move around, and it says they come back the same orientation that you see in the picture here once in 18.6 years. And then careful calculation showed that this is because Sun is also affecting the Moon's orbit gravitationally. It is not just the Earth alone which is responsible for the Moon's orbit, but major contribution to Moon's orbit comes from the Earth's attraction. So the Sun's attraction, gravitational attraction, plays the role of a perturbing force, a small deviation, and Newton was able to actually calculate this small deviation and exactly account for the motion of the nodes of the moon. Now, the important thing is this. It showed that small perturbations can also move something like nodes. But please remember, these nodes are not physical points. They are imaginary points in space. But he said, Newton said that it can also be applied equally to anything that has mass, and the motion of that mass would also be following the same principles. And that is how he solved the problem of ocean tides. So this picture is all that we would need for a simplified understanding of tidal force. And this P, the point P is the center of the moon, point A is the center of the Earth. For simplicity, we consider that these two are perfectly spherical bodies, and the force of attraction, gravitational force of attraction, is between the center of mass of the Earth and the center of mass of the moon. Let us take the distance between these two centers to be 1 unit. Then the distances of different points on the Earth from the center of the moon is shown on your screen. So what you find is that the distance between the center of the moon and different points on the Earth, like point C, which is nearest to the center of the moon, point A, which is at the center, therefore it is farther, and point B, which is still farther than point A. Because Newton's law of gravitation tells you the force of attraction is inversely proportional to the square of distance, as the distance changes, the force of attraction will be different. That is, the force with which point B attracts point C is more than the force with which point B attracts point A, because C is closer to B. By the same token, point B attracts point B with lesser force than point A. Now, if you take points A and C, you'll find that there is a difference in the forces of attraction. This differential force of attraction is what we call tidal force. Right at the beginning, I mentioned that tide is related to three different things. One of them is tidal force or a differential force. So, tidal force is a differential force. So, if you take the difference in the force of gravitational attraction at 2 points, that difference will give you tidal force. And one point of reference is the center of the Earth, and the other point is any other point on the surface of the Earth. It can be even inside the Earth, but for simplicity, we take only the surface of the Earth. With the same picture that is written here, it is a very simple mathematical derivation, and anything that is simple will tell you that we have compromised on accuracy. So we have compromised on details, but we have not compromised on the essence. So the core idea remains the same. So this point is the center of the moon, and it is at a distance d from the center of the Earth, and r, small r, is the radius of the Earth. Now we can find the force of attraction at the points C, center, point A, closest to the moon, point B, farthest from the moon on the Earth. And in each of these cases, we use Newton's law of gravitation, which is g_mm by d square. But the d will be changing in each of these cases. For the center, it is d. For point A, it is d minus r, because it is closer to moon, a distance equal to the radius of the Earth. And d, it is d plus r. Capital D point is at a distance d plus r, because you have to add radius of the Earth, because that's the distance that is away from the center. If you take the tidal force at A, you just have to take the difference of the force of attraction at C and A, and you do a little bit of algebra and approximations. You find that this tidal force is proportional to 1 by d. Actual expression is 2d_mm by d cube into radius of Earth. This is the tidal force at A on Earth due to the moon. Okay? So we will go back to equation 1 that I referred in the previous derivation. So we have here the tidal force at A, which is proportional to 1 by d cube. Tidal force is also proportional to radius of the Earth, as you see from the equation. It's 2g_mm, mass of the Earth multiplied by mass of the moon, they are all constants. What does this imply? This implies a very, very important thing. Since majority of your students, I would like to impress upon you this particular point. The point is this, that tidal force becomes evident only when you consider an object of a particular size. When you solve problems in mechanics, very often you take point objects. So what do you mean by point objects? You don't get point objects in the universe. Nowhere you have point objects. A point object is an approximation you make. It's a mental model of the object you make. But telling yourself, look, in order to solve this particular problem, I don't need to know the size of the object. So if you want to know where Mars is today and where Mars will be 5 months from now, use Newton's law of gravitation to do the calculation. But you don't have to know how big Mars is. You put any object in place of Mars and it will follow the same displacement in 5 months. Therefore, there are certain phenomena in which size does not matter. For the application of Newton's laws of motion and Newton's law of gravitation, the size of the object is not important. But tidal force, which we have calculated on the basis of Newton's law of gravitation, clearly tells you that size of the object does matter. So this is a very important point. So point objects cannot show tidal force. Put radius of the Earth equal to 0, then the tidal force becomes 0. There's no meaning to it. Okay. And the second point is that tidal force is inversely proportional to the cube of the distance. This is important because we calculated the tidal force on the basis of gravitational force. But gravitational force is proportional to 1 by d square, but the tidal force is proportional to 1 by d cube. What this means is the tidal force, okay, so the tidal force falls down sharply compared to gravitational force. So that is the effect of 1 by d cube. Okay, we should observe that. We'll come back to that point a little later quickly. Gravitational force between two objects will be equal. Vmm by r squared. So the distance between 2 points is commutative. The masses are being multiplied. Therefore, gravitational force of attraction of Earth on Moon and gravitational attraction of Moon on Earth will always be the same. What about the tidal force between these two objects? Will they be the same? Actually, they will not be. It is for the following reason that in our expression for tidal force, there is this radius of the object on which tidal force is being calculated. So if you want to calculate the tidal force of Moon on Earth, you take the radius of Earth into account. When you have to calculate the tidal force of Earth on the Moon, then you have to take the radius of the Moon into account. Now, radius of the Moon and radius of the Earth are not one and the same. In fact, Moon is just about 1/4 of the radius of the Earth's radius. Therefore, tidal forces do not form an action-reaction pair. Because we are habituated that when we talk about forces between two objects, they are always equal and opposite. But in the case of tidal force, that is not the case. So, tidal force of Moon on Earth is actually larger than the tidal force of Earth on the Moon, simply because Moon is much smaller than the Earth. Now, the tidal force also depends on distance. It's the inverse cube of the distance, so that we discussed. If you actually look at all the data that people like Pliny, Poseidonus, and Eratosthenes had, clearly told that Sun's tidal force contribution is much smaller than the Moon's contribution. Of course, they did not say so openly, they were not aware of Sun's contribution. Now, this comes actually from the present day knowledge. So I'm just giving it to you as a fact to start with. The Sun's tidal force is roughly half of what the Moon exerts. So even though there are two questions to this particular observation. Number one, Sun is so massive. It is something like 330,000 times the mass of the Earth. 330,000 times the mass of the Earth. And the Moon is roughly 1/100th of the mass of the Earth. Therefore, the mass of the Sun is so much more than the mass of the Moon. Yet its tidal force on Earth is only half of the Moon. Why should it be like this? So the inverse cube of the distance is one of the factors. But what is surprising here is that whether sun is half of a moon's tidal force or not, they are of the same order of magnitude. It is not 10 times more or 10 times less or 100 times more or 100 times less. It is of the same order of magnitude. Now, why should they be of the same order of magnitude? Can we easily understand this? And again, because a large composition of today's audience is undergraduate students, I would like to show how easy it is to demonstrate this point, why the order of magnitude of sun and moon tidal forces are nearly the same. So go back to the derivation for the tidal force. We have 2 g into radius of the earth by d cube. All you have to do now is take the mass of the moon, replace it by density by volume of the moon, and do a little bit of algebraic shifting, manipulating the expression, and you get the expression that is at the bottom, 4 by 3 pi capital G mass of earth into radius of earth, all constants, into 2 times. So I have deliberately taken inside the bracket, inside the box, red box, and you have the radius of the moon by earth-moon distance, cube. So the term which is in the box, 2 times r by d, is the angular size of the moon. Now, if you put, instead of radius of the moon, if you put radius of sun divided by distance of the earth to the sun, then it becomes the angular size of the sun. A total solar eclipse happens only because the angular size of the sun and the moon are the same. Therefore, angular sizes are the same. So what remains outside is a constant, capital G, mass of the earth and radius of the earth. And because the angular sizes of sun and moon are the same, the tidal forces also must be nearly the same. Okay, so that explains how the order of magnitude of sun and the moon is roughly the same. Okay, so there it is. There is one more trick that you can do. Remember that 0.42 that we got for sun's contribution? You can again do it from the simple equation from the tidal force. Just take the ratio of the tidal force of sun due to sun and due to moon. Common factors like 2d and mass of the earth will cancel out. And from the remaining ones, the angular size will be there. Angular size will also cancel out because angular size of the sun and the moon are equal. So what will remain outside the bracket is just the density of the sun divided by density of the moon. So if you divide the average density of the sun by average density of the moon, which is 1.41 by 3.34, the ratio comes out to be close to 0.4. So you can use very simple algebra to get a lot of information about tides using nothing more than Newton's law of gravity. Right? But in all those equations, you have the mass of the moon sitting. If you want to know the density of the moon, you need to know its mass. Or if you want to directly calculate tidal force, you need to know the mass of the moon. But for want of time, I may not be able to discuss in detail. I will skip a particular slide here, but I'll just leave it as an exercise to you, saying that determining the mass of the moon is very, very difficult compared to determining the mass of Jupiter or mass of the sun. Simply because these two objects, Jupiter and Sun, have some objects going around them. And you can use Kepler's laws of planetary motion to reduce the mass of the body. Moon has no satellite. Of course, these days you have artificial satellites like Chandrayaan 1 or Chandrayaan 2, which will be going around the moon, and you can actually find out from their distance from the moon and from their period of revolution, you can estimate the mass of the moon. But just about 100 years back, that was not the case. Again, using tides, it is possible to determine the mass of the moon. and it requires nothing more than high school algebra. So it is for that reason I am showing this. But there are other ways which I leave as an exercise to you people to find out. Okay. Now, there is something called spring tide. Spring tide is the high tide you get when Earth, Sun, and Moon are all aligned in a straight line. Okay. So this happens at full moon or at new moon. Then the angle is 180 degrees between Sun, Earth, and Moon. There will be a certain tidal height at that point of time. Then there is something called neap tide, which refers to when the Sun, Earth, and Moon are nearly at right angles, which means when the Moon is right above your head in the sky, the Sun is either setting or rising at the eastern or western horizon, and it makes an angle of 90 degrees. At that point, the local high tide is taken, which is called the neap tide. Okay. Now, whatever the tidal height of the ocean, it is because of not just moon alone, it is also because of the sun. But we don't know what is the contribution of the sun and what is the contribution of the moon separately. But you can actually measure the tidal height at spring tide and neap tide. So let us take the two heights to be x plus y and x minus y, x due to sun and y due to moon, or the other way. Now x plus y, you take it as 100, and x minus y will be 42. Now these things come physically from observation. If you look at the tidal height, you get this ratio 100 by 42. Now we know from Newton's law of gravitation, the expression for tidal forces is, when you take the ratio, you get what you're seeing on the screen, mass of the sun by mass of the moon, multiplied by distance cube of moon by distance cube of sun, because it's inverse relation. Then we also take the reciprocal of the above fraction, 29 by 71. So from this, we know the distance to moon, we know distance to sun, we know the mass of the sun. So just the mass of the moon can be calculated, and that comes out to be 1 by 80th of the mass of the Earth. See, doing nothing more than observation of tidal heights at full moon and at the first quarter moon, and knowing a little bit of Newton's law of gravitation, it is possible to determine the mass of the moon. That is the power of any theory. So the theory of gravitation did not just tell how two objects attract one another. There are plenty of other phenomena that came out to be understood by virtue of Newton's law of gravitation. I'll just mention in passing that just like ocean levels increase and decrease, levels in atmosphere also increase and decrease, called atmospheric tide. But in the same way, even there are solid tides, the whole land mass of the Earth goes up and down. But please remember one thing. When the moon is exerting a tidal force on Earth, it is not doing one at a time on ocean, on atmosphere, and on land. It is a contribution by the land below that as well. The whole ocean bed is lifting up, along with that, the ocean level is rising. But what you are measuring is only the ocean height. You do not know by how much the land height has increased. It's another story how you can separate out the effects of land tide and ocean tide. It's a lot more complicated, but it has been done by people in the past, ingenious method. If there is time, I'll come back to that during the question answer time. Otherwise, I'll skip for the time being. Okay. Now, again, because we have a large composition of undergraduate students, I wanted to just mention in passing that the whole idea of understanding tides is done by looking at oscillations like a simple harmonic oscillator of a spring mass system. I must tell you, even simple harmonic oscillator is very complex if you take into account various factors. And understanding tides is a million times more complex than understanding the most complicated simple harmonic oscillator. But people have done it. There are mathematical tools to understand. But I just wanted to show you the direction in which you have to think in order to understand the tides and appreciate it. Okay. Now, there are one or two points before I come toward the end of my talk. People have observed, in fact, Pliny had observed that a high tide in a place occurs a little after the moon has passed the meridian locally, and it is not surprising. It is because as the water level, the ocean levels go up and down, and Earth is rotating along with that, there is a huge amount of friction that is developed between the moving ocean and the rotating Earth. So because of this friction, there will be a phase lag. And again, this is like a simple harmonic oscillator. Suppose you have a simple harmonic oscillator. Suppose it is driven by another oscillator. There is no frictional loss. Then depending on the frequency relation, it can be in phase. But if you put friction, then there will always be a phase lag. It will be a little behind the driving force. That is, after the driving force has achieved maximum, it takes a little time for the driven oscillator to come to a maximum amplitude. And that is the physics that goes into understanding the tides. And we actually see that high tides occur a little after the moon has passed the meridian locally. Now, because of this, what happens is the ocean bulge is not strictly in the same direction as a line joining the center of the Earth and the Moon. Okay, imagine a line joining center of the Earth and center of the Moon, and then there is a tidal bulge which is at some angle. This brings about a very, very important consequence. What is that? That actually applies a certain amount of torque on the Moon. Okay, so the Moon is causing a bulge on the Earth, ocean bulge on the Earth, let us say, and this bulge should have been strictly in the direction of the center of the Moon, but it is slightly away from the Moon. It is lagging in phase, but because of the rotation of the Earth, the bulge is actually dragged along and it goes ahead, and this causes a lot of friction. And because of this, the bulge and the line joining the centers of the Earth and the Moon, they are not aligned. This actually causes a torque on the Moon, and that torque, your basic physics tells you, will cause a change in angular momentum. The angular momentum of the Moon changes because of this, it increases. But because the Earth and the Moon act like a single system, the total angular momentum should be conserved. So whatever the torque that is created by the Moon on the bulge gives back to the Moon by the same torque, and that torque increases the angular momentum, and this results in the Moon going away from the Earth all the time. So the Moon's orbit is always expanding. And this particular point was first calculated by G.H. Darwin, son of Charles Darwin, the evolutionary biologist. So he had actually calculated, and he showed that because of this friction between the ocean tide and the Earth's rotation must be slowing down. And because the Earth's rotation is slowing down, that lost energy must be put back into the Moon's orbit, and the Moon should be going away. Okay, and the actual calculation that he did showed that Moon should be going away from the Earth by as much as 3 centimeters per year now. How do you find out if the center of mass of the Moon has gone away by 3 centimeters? Because the size of the Moon itself is something like 1,500 and odd kilometers, plus or minus 3 centimeters should not be visible at all. The interesting thing is we have been able to measure even that very precisely. And for that, we use a laser. Okay, a laser is a shot from the observatory, like you see on the left-hand picture. The pulse, actually, a pulse of laser, it hits the moon and comes back. But how does the moon know to reflect this light back to the observatory itself? Moon is a diffuse reflector. So this pulse will be reflected in all sorts of directions. The probability of reflected pulse coming back to the observatory is very, very small. So what people did, or Neil Armstrong did when he landed on the moon in 1969, was to place this small gadget which you find on the right-hand part of your screen. It's a retroreflector. It is made up of 3 mirrors which are at mutually right angles to one another. Okay, so it is like this. So you have the plane, this is right angle, and you think of one more right angle there. And the beauty of this geometry is that to shine light at any angle, reflected light will always be parallel to the incident light. So we know exactly where this has been placed, and people send a laser pulse to that, and it reflects back to the observatory. And from the constancy of the speed of light, you can determine the distance to the moon. And the determination accuracy has yielded now that it is going at the rate of something like 3.4 centimeter per year, precisely as G.H. Darwin had theoretically calculated. You should remember, Darwin did this calculation almost 100 years back, long before the space age began. Okay, but we have been able to verify this. This is the beauty of a good theory. A good theory will always predict something, and it's only technology which will make you to conduct experiments and verify if the theory is whatever the theory has predicted can be observed. Okay, so the consequence of this is that the Earth's day is slowing down. Now, this is where Edmund Halley comes back into the picture. Now, Edmund Halley's ancient eclipse records, as I told you, showed a systematic variation in time. Suppose he calculated that in particular place in Babylonia should have had a total solar eclipse at 3:10 p.m. There would be a record which tells that it did not happen at 3:10, but it actually happened at let's say 3:08 p.m. So this kind of variation between the documented record and the present day calculation shows that the Earth's rotation rate must be changing. And that is where Halley's work is very, very important. But it is one thing to say that in order to match the records, you have to assume that the time Earth rotation has changed, rotation rate has changed, and Earth's rotation is what gives us a fundamental clock of 24 hours. So if time taken for one rotation changes, then the length of the day changes. So much so that 400 million years ago, if you actually calculated the rate at which the Earth is slowing down because of tides and other factors, it was just 22 hours long, assuming that 1 hour of today is what was 1 hour of that day. Okay, so this is a mind-boggling idea. But again, this is theory. How do we prove that 400 million years ago a day was 22 hours long? This time, the solution actually to this question comes from not physics or astronomy, but it comes from biology. That is surprising. So there was this person, a paleontologist by name John West Wells. He was studying the fossil of corals in 1963, and he found, these corals have these bands, as you can see on the bottom picture on your screen. These bands are the deposits of calcium that these corals actually form, and for that, the length of the day is important because it's a reaction that happens in the dark. So the length of the day decides the length of the bands and also the number of bands. So all that John Wells did, it's easy to say all that he did, but it's a very complex thing that he did. To take present-day coral of the same species that you have a fossil of, when you count the number of bands and the band gaps between the two, fossil and the present-day one, and the difference will tell you the difference in the length of the day. And lo and behold, it turns out that in these fossils, we find that Earth's rotation rate was much faster in the past than it is now. So Earth is actually slowing down at exactly the same rate that Darwin calculated based on classical mechanics and law of gravitation. And evolutionary biologist and paleontologist John Wells actually comes up with a number which matches with what Darwin had calculated. This is a beautiful way of doing science, don't you think so? So if you are going to do physics, you'll be a better physicist if you have a good background in other sciences as well, especially biology. So I'll quickly go over the remaining part because the basic foundational things I have discussed now. Because the Earth is using energy, because the Earth's ocean bulge is acting a tidal torque on Moon, because of which Moon is going away, so the Moon's orbit is expanding, and Kepler's laws will tell you that as the orbital distance increases, the period of revolution will become smaller. It takes longer time to complete one revolution. So now, Moon is at such a distance that its period of rotation and period of revolution is exactly the same, 27.33 days. So because of this, the Moon shows the same side to us, because even though it is rotating, it's revolving, its revolution is also at the same period, and because of that, there's what is known as a synchronous rotation. So the right-hand picture actually clarifies how it happens. Therefore, for people who are on the Earth all the time, the other half of the Moon is never ever visible, only because the period of rotation of Moon is same as the period of rotation of revolution of the Moon. And all this because of the tides. So tide is the one which is responsible for the synchronous rotation. And if you could actually leave the planet Earth and go around the Moon in a satellite, you'll actually find the dark side of the Moon, which is also very brightly illuminated by the sun. So dark is only a metaphor. One consequence of Moon moving away is that its angular size will slightly decrease. So there may come a time in future, not in your lifetime and my lifetime anyway, in distant future, when the Moon's distance will be so much that its angular size will be much smaller than the angular size of the Sun. And that is when total solar eclipses will never happen. So at most you will have an annular solar eclipse like we are seeing on the picture here, taken by one of my students, Mr. Naveen. There will be no total solar eclipses at all. So you will miss the diamond ring and all sorts of things that we associate with total solar eclipse. Okay, and this is a table from Wikipedia. You can also find out from wherever I stole it. It tells you that Moon is not the only object which is tidally locked with the Earth. There are so many objects which are tidally locked with the Sun and their parent planets. This is an interesting physics by itself, but not beyond a UG or a PG physics student. So please do study about them. And tide has a very important impact on biology. So I would like to quickly go over this and one more aspect in next 5 minutes, and I will close down my presentation and I'll be open for questions. Now, as this tide keeps increasing and decreasing the water levels, there is a huge amount of friction with the rocky bed of the oceans and seas. And this friction actually removes layers of these chemicals, and as water is pushed to the shore, all the chemicals which are locked in one place are transported to another place. So all the life important biomolecules which are locked in these rocks underwater are made available on the land as well. So tides actually enrich the chemical environment of the seas, oceans, and as well as land. So if life has to flourish on, even primitive life has to flourish on land, all the important biomolecules which once upon a time was part of aquatic life should also be available on land. For this, transportation of material is important, and ocean tides have done this job very, very efficiently. Not only that, just as the tides have a rhythm, there is a high tide and a low tide happening at a particular periodicity, and from one day to another day there is a continuous shift. Now these aquatic organisms like the fish or the crab or corals, if they did not adapt to high tide and low tide timing, they would become extinct very soon. Just imagine that you have this particular fish. Actually, the spawning of this Bruneian fish happens only at low tide when they are all brought to the shore. And after the spawning, which happens in thousands and thousands at a time, they have to be ready to go back with water at the high tide. If they did not swim back in time, they'll be left back on the shore and they die. Therefore, there must be some kind of a rhythm in their body which follows the high tide. In fact, I'm not sure if it is the same crab, the Anamuran crab that you see here. I'm not sure about this. One of the professors, who is no more now, Professor M.K. Chandrasekharan, is very well known for his work on biological rhythms in organisms. What they found in a fantastic experiment was that if you brought a crab from an ocean and you put it in a big aquarium in your laboratory, this particular crab will actually go to the surface and then go to the bottom of the aquarium, mimicking the same periodicity as the high tide and the low tide from the ocean where it was brought. So there is some way in which it has learned to live with the periodicity, and which is very, very important for its survival. So tides are not only important for us in many ways. For example, fishermen should know when high tides occur, when low tides occur. But for these animals, it's a matter of life and death to know the periodicity of these tides. So finally, I end with the astronomical consequences of these tides. So tides are not just something related to Earth and oceans. Like I told you, it's a differential force. Any two objects which have a gravitational attraction between the two will exert tidal force also. Now, it is because of this tidal force, which is a differential force, it can make objects actually tear down into small pieces. The rings of Saturn that we see, according to one theory, it goes like this. There is an object pretty close to the sun, and the tidal effect of the sun on that object, the differential force was such that the object was actually torn apart. So whether an object is torn apart by a particular amount of tidal force, it also depends on the rigidity of the body, whether it can respond to the tidal force, expand, and then again contract. So rigidity also plays a role. So from these small particles that are there around, James Clerk Maxwell actually calculated the tidal attraction of Saturn on a fictitious planetesimal during the formation of the solar system, during the formation of Saturn, and he showed that tidal forces could have been large enough to break them into pieces, and the rings are because of are the result of the tidal force. A close-up of rings show you those tiny. These are real pictures taken by Cassini spacecraft. Small pieces of rocks. So once upon a time, all these rocks were held together by gravitational force. So don't think it's an irony that gravitational forces bring things together. A differential gravitational force, the tidal force, can actually rip them apart. This is one of the satellites of Jupiter, Io, again, the tidal forces because of Jupiter and some of the other nearby satellites is so huge that the entire land mass of Io goes up and down by 100 meters every day. Every day on Jupiter. On Jupiter, one day is 10 hours, as you know. So constantly it is being lifted up and then drop down, lifted up and drop down. This causes enormous amount of heating, and that heat is so much that sulfur deposits underneath, they melt and they come out as a volcanic eruption. So this bluish area that you see on top, it's false color actually. That is actually the sulfur volcanic eruption from planet Io, satellite of Jupiter, Io. Interacting galaxies also are torn apart, and many irregular galaxies that you see are distorted and twisted out of shape. They are all the results of such um, tidal interaction in the past. Now coming to the Shoemaker-Levy comet. So this comet actually came pretty close to Jupiter, and the tidal force of Jupiter was strong enough to rip apart this particular comet into pieces. And all these pieces, one by one, they banged on Jupiter, and that was the end of it. And in the realm of black holes, tidal forces become extremely dangerous. Dangerous only from human point of view, but otherwise it's a natural thing. Let me see if I can run this video. There is a black hole here, on the left-hand side. If there's a nearby star which is in a red giant phase where the mass has extended, then this tidal force of black hole can actually cause all the matter to be transferred towards it. This is what is responsible for the formation of accretion disk around the black hole. Now, it's the tidal force of black hole which causes matter to be transferred. And the matter transferred is a signature that there's a black hole sitting. Otherwise, there is no way of directly knowing where the black hole is. But if you see an accretion disk around a point, then you can be sure that there is a black hole. So tidal forces can also be like a signature of a black hole. And I finally end with what has been in news in the recent past. That is the gravitational waves. Okay, so when you have two black holes or two neutron stars or a neutron star and a black hole, in short, two compact objects going around in a binary system like that, they produce enormous amount of tidal forces on one another, and it is that which is responsible for the formation of gravitational waves. Gravitational wave, strictly speaking, is also a tidal wave, except that the rise and fall of this amplitude of the gravitational wave will be of the order of rotational revolution speed of the two interacting black holes. And they are detected on the ground. You need huge detectors there. The one in Hanford is 4 kilometers long. Each arm is 4 kilometers long at right angles. And these tidal gravitational waves produce very, very small reflections in the mirrors there, which can be detected through interference of light waves. So in short, physics of tidal tides and tidal waves that we demonstrate can be extended all the way to different size scales, different distance scales, and also into different parts of the universe. So studying tidal forces and tidal interaction is one of the most significant areas of research in all of cosmology, because they give the clue about various kinds of interactions that are happening on an astronomical scale, cosmological scale, and tidal forces are the only signatures that we can detect from the Earth. Gravitational interactions are very hard to detect, other than seeing them move around. But other processes can be understood only through study of tidal interactions. So, to summarize, tides are extremely important ideas. They're not just as simple as ocean tides that we see. Ocean tides are not very simple, but physics of understanding the ocean tides leads us all the way to understanding gravitational waves, and that is the significance attributed to this. For all the budding researchers in physics sitting out there listening to this talk, I have highlighted, hopefully, the significance of understanding tides, but it's very unfortunate that tides are not given the kind of textbook treatment that it deserves. Most textbooks don't discuss tides at all, and a few discuss, and very superficial. You should be ambitious. There are references on the screen. You can go over these references. So I have used these references profusely for my talk. And I thank Atul Bhatt, Dr. A.P. Bhatt, and all his team members of Poornaprajna Astronomical Club for this opportunity. Thank you.